Okay, hello everyone. I wanted to go over one of the other topics here, which is hopefully a fairly short one because it has a lot more to do with not anything new fundamentally, but manipulating concepts that hopefully we're already aware of. And these concepts are related to supersonic and transonic flow. There are a couple of important major things that we need to do fundamentally differently, and those involve how we select our physics. So there's two different things you need to do for this. You need to make sure you've already done one thing that we've done before, which is make sure your physics are using ideal gas. And the second thing is we need to use coupled flow instead of segregated flow. If you use segregated flow, you might be able to get into the very low transonic or supersonic, but it's not going to be very efficient. It's not going to be very stable in general. Really, to do true supersonic stuff or even hypersonic stuff later, you need the coupled flow solver. The rest of our selections are probably pretty good, but you definitely need coupled flow and you need ideal gas. So one thing to realize is that you might have supersonic flow even if you don't realize it. Even if your boundary conditions aren't set to a Mach number greater than 0.1, you can still have shockwaves and everything. So I've set up a case here to demonstrate this where we have... Hold on, let me hide this really fast. Stop this from iterating so I can actually hide this. There we go. I've set up our two-dimensional airfoil, our NACA 4412, at Mach, let's see here, 0.85. So a couple things I changed. Instead of having these outlets be pressure outlets, I've made them free stream outlets. Theoretically, they could still be pressure outlets. Shouldn't matter too much. But because in specifically true supersonic flow effects only propagate downstream, having these boundaries be free stream condition is actually probably okay. If your velocity or your shock wave makes it all the way out here, that's not a big deal because it's not really going to affect the airfoil. The second thing is this is a Mach number of 0.85. It's not even a Mach number of 1. But we very clearly have shock waves. And this is where it gets into the next thing, where we don't necessarily have to explicitly change anything we're doing, but we have to go back to remembering, how does meshing work? Where do we need cells? Well, the answer is you need cells where properties change rapidly. For an airfoil, that's at the leading edge, the trailing edge, little ways along the surface, but with most subsonic cases, you don't really have large changes. You don't have large gradients for at least something basic like that, like an airfoil. However, when you go supersonic, even if your initial conditions or your boundary conditions aren't supersonic, when you have shock waves, you have very, very rapid changes, very small distances. Let's take a look at this for a second. So I've gone ahead and done a little bit of a fancy thing here. I've taken the gradient, the magnitude of the gradient of static pressure, and I'm showing cells where that is higher than 5 times 10 to the 4. This is where pressure is changing very rapidly. We can see that it exists in very clear shockwave delineated patterns. If we look at the velocity, we can see it's in the exact same places, where the flow is suddenly exchanging kinetic energy for pressure energy and temperature as well. Let me go ahead and pull up a couple of more scalar plots, and let's take a look at this real fast. So this is going to be a temperature scalar plot. And we can see very clear differences in temperature here. It's still kind of figuring out the boundary conditions. This hasn't run out all the way. But we can see very clear and sharp temperature differences where shockwaves exist. If we go over here and we plot static pressure, we can see similarly large, rapid changes in static pressure across these boundaries. We need a mesh that's fine enough to resolve these. Because if you don't have a mesh that's fine enough to resolve those, you're not going to resolve any of the shock waves, or at least not very well, which isn't going to give you accurate results for supersonic cases. So you need to think about how can you get these cells where the shock waves are. In 2 dimensions, which we're doing for this example, it's relatively simple to just kind of throw more cells at the problem. That can absolutely work, because 2-dimensional computations are relatively inexpensive to run. And you can do that with your typical refinements. What I've done here is shown one example of this. Of a conical refinement region with a void. So we could have just refined this entire cone. And I made it refine this entire cone by making a cone, making a second cone, and then cutting away the second cone from the first cone with a subtract operation, which creates a cone with a void in the back. You can see this cut out in the back of this cone here. And in order to execute this refinement, I did a volumetric control, saying everything where this cone exists, or this hollowed out cone exists rather, go ahead and refine the mesh. Specifically, I made the target size, I believe 50% of the base size for this region. And we can see it very neatly made a region that doesn't quite entirely, but mostly encapsulates where those gradients are really high. That is one way to do it. You can also figure out where your gradients really are going to be quite high by doing something a little bit fancier. But before we go into the fancy stuff, let me just zoom out a little bit and basically mention that, or highlight the fact that, again, the important thing with supersonic flow is you capture the shockwaves. You need a fine mesh where you have shockwaves. Because shockwaves very rapidly change properties in very small distances. If you don't have a good mesh, you're, at the very minimum, you're not going to get valid results for where the shockwaves are or how strong they are, which is going to throw off all of your parameters of interest. Your maximum and minimum temperatures are going to be wrong. They're going to be in the wrong place. Your maximum and minimum velocities are probably going to be wrong. Ditto static pressures. All your properties are going to be wrong, or maximum and minimum in the wrong places, which is going to get you erroneous lifts, erroneous drags, and generally throw off your results. You need to resolve where the shockwaves are to a reasonable degree of accuracy. If you want to sort of sanity check where the shockwaves are, you have a couple of ways to do this. You can just plot velocity or pressure, run your simulation for a little bit, and see where you get sharp discontinuities like this. This gives you a pretty good idea of where that shockwave is. Alright, we have actually kind of staggered shockwaves because this is a relatively complex transonic flow problem. However, we can get a little bit fancier still. This is where I'm going to introduce custom field functions. So, a field function simply represents a property in space. A field function is a value that exists in 2 or 3 dimensions depending on your simulation. This could be things that you already aware of, like pressure. Pressure changes from point to point in the simulation. Velocity changes from point to point within the simulation. Density, temperature, all of these are values that vary. Mach number, that vary from one point to another. So you can see a list of all the field functions you have access to down here under Tools, under Field Functions. Now again, things like absolute pressure, total pressure, temperature, velocity, velocity components, etc. These all exist in space. They change from point to point. And that is a field function. Now you'll note that I called out velocity and pressure. Well, clearly one of these is a vector and one of them is not. Field functions can be either, or they can be even more advanced. So you can have vector field functions where the magnitude and direction changes from point to point. Or you can have a scalar quantity where there is no direction. It's just the magnitude varies from one point to another. Again, static pressure, Mach number, these are scalar quantities. Velocity, some other related things, are vector quantities. They have magnitude and direction. We're not constrained to what they give us, though. We can create our own field function. This is a bit more of an advanced topic, and this is kind of one of the things that really we want to get to in a course like this, is some advanced abilities to manipulate simulations. So, field functions. You can create new field functions. It can be a scalar field function, a vector field function, a symmetric tensor, a position, an array. You can create all kinds of them. We're mostly going to stick to scalar and vector. So let's go ahead and take a look at a scalar field function. You can create a new scalar field function. You can see that it's by default called user field function. And it has the property that, or has a value type of scalar. And it starts out as dimensionless by default. And it's also defined as 0 everywhere by default. I'm going to create a new scalar scene. And we're just going to plot our field function we just made. User field function 1. Now it's 0, literally 0, everywhere, because we haven't defined it yet. So we've got this graph up. It'll show us what this field function looks like in different places. Let's look at how we define it. This is the definition under properties. So we have many things we could do. We could plot the cell aspect ratio, for example. This is plotting the aspect ratio of cells. That's nothing fancy. We could have absolutely plotted that without making a custom field function, because that's an existing field function. But we've defined, in this case, our new field function as a already existing field function. Okay. Nothing particularly useful about that just yet. Let's see here. However, we could do something like divide our cell aspect ratio by volume. Now, it doesn't look like this is telling us anything all that much. But if we look real close, we can see that for some of the cells that have extremely small volumes and high aspect ratios, or low aspect ratios rather, some of these cells have extremely high values that really stand out from the crowd. Most of them are pretty benign, but if you wanted to locate regions where you had simultaneously low volume and high aspect ratio, this would show you. We could also take the inverse relation and say 1 divided by just changing the definition here in line here. We could flip this on its head and look at values where it has high volume and a relatively low aspect ratio. So, unsurprisingly, it's really just showing us the largest cells in the simulation, combined with their aspect ratios. And all the smaller cells are something like that. This can be useful, for example, if you want to know where the ratio of density and temperature has a particular value or something. However, you can also do some fancy things. Let's say we want to know where exactly is pressure actually changing very rapidly. You could absolutely plot this and look visually and see where there's large changes in pressure. But we can see this potentially even more precisely, because you can do fancy things like take the gradients of vectors, take the magnitude of vectors, or the gradient of scalars, excuse me. So let's say we want to take the gradient of static pressure. Well, we have several functions we can do here. You have all the usual trigonomic identity or trigonomic functions, sine, cosine, etc. You can take the magnitude of vectors. You can take the double magnitude of vectors. You could take the unit vector of a vector. You can take dot products, cross products, curl. You can take the divergence of a vector. You can do things with tensors, eigenvalues, dot values, or dot vectors, eigenvectors, eigenvalues, etc. You can do things with tensors. You can also find various things like the absolute value of a scalar, the floor value for a scalar, the ceiling value for a scalar. You can take the log, either natural or base 10. You can take the square root of a value. You can raise a value to the power of another value. You can do min, max, and for this purposes, one of the more useful ones, we can take the gradient. Well, we can take the gradient of, let's say, static pressure. This is actually going to be a vector quantity. The gradient of a scalar is actually a vector. It tells you how much it's changing per distance, gradient, but it also tells you the direction of the maximum rate of change. The gradient gives you a magnitude, the rate of change, and the direction in which its maximum change is occurring. That's a vector, right? You have magnitude and direction. So if we did this right now, it would yell at us because we told this is a scalar. Oh, yep, field function, type and definition are inconsistent. It's like, hey, you told me I'm a scalar. I am a scalar. But I'm also a vector? This doesn't make sense because the gradient is a vector quantity. So we can also, this is one of the other more useful operations, is we can take the magnitude of a vector. So if we put the gradient inside of the magnitude function, suddenly we have the magnitude, which is a scalar value, of a vector. That's absolutely a scalar value. We can plot it. We're plotting the gradient of static pressure. We could also change this and do something else. We can plot the gradient of, let's say, temperature. Okay. Well, it's not showing us very much because almost everywhere the gradient's actually quite small. Let's go ahead and try and look at where these values actually exist. We can see that this simulation thinks the maximum value, based on this color bar, it thinks the maximum value, I say think, it knows the maximum value is 1.06 times 10 to the 6. It knows the minimum is 0.00127. And most spots in this simulation are much closer to the minimum than the maximum. We want to actually see where this value is more in the middle here. So we can modify our scalar field limits. Instead of plotting our min and our max as automatic, we can manually set them. So let's go ahead and set this minimum to something like 1e to the 4. Well, this doesn't actually change anything because this quantity, clip. What clip does is it tells you, hey, if a value is below the minimum or above the maximum, do I show it? If you tell it to clip values below minimum, it won't show anything below the minimum. Notice how all these cells just disappeared. If you clip above max, it will clip everything above the maximum. Let's do 1e to the 5 and try and find a couple of cells that are missing here. But it's actually possible to see it cut out this very first cell. 1e to the 4. You can see it cut out some more cells. It's not showing anything where the maximum value is above 1e to the 4. And we can see where some of these shock waves are forming a little bit based on this gradient. Now, this is a gradient of temperature, or the magnitude of gradient of temperature. It's not the most useful thing in the world. I'm going to go set it back to static pressure. That is a lot clearer. Let's take a look at this. Well, that's one hell of a gradient now. Exactly what we wanted. So let's tweak the scalar field a little bit more. I'm going to tell it auto range. I'm going to have it go ahead and auto range both min and max again, so we can see what the minimum and what the maximum is. Well, I'm not going to want to show most of this because this is all just blue. So let's start walking this value up. 10, it cut out a few cells. 100, it cut out a lot of cells. 1,000, well, many more of them. 10,000, getting there. 100,000. Well, let's do 8e to the 4 and look at something slightly less than 100,000. And also, we're going to plot 1e to the 6. So we can see a little bit more of a reasonable range here. So we can see, based on this pressure gradient, took a little bit of trial and error to get. We can see where the highest pressure gradients are. We have a very high pressure gradient up here, near the stagnation point. That's not unexpected. We also have very high pressure gradients in this shock wave. This is where we need lots of cells in order to resolve. Lots of cells. And so that's why we put some of these cells specifically here. We didn't know exactly where it was going to be, so we kind of had to brute force it a little bit. But we added a whole bunch of cells where we expected these shockwaves to be. That's one thing you have to do for supersonic airfoils. And we could visualize where these shockwaves are multiple different ways, just by looking at velocity contours. Looking at... let me actually make this static pressure again. By looking at static pressure contours, you can see where these quantities change rapidly. And again, you can have supersonic flow even if you don't have supersonic inlet conditions. That absolutely can happen. And actually, I think I might have messed up my boundary conditions. Or it's just simply not done. Ah. I'm not exactly sure why it has a much lower pressure over here. That's a little bit perplexing. Let's just check our reference pressure really fast. Be fine. It might have to do with the initial conditions that got set. But any case, so this is a transonic case. Again, we have to watch the shockwaves, figure out where they are, and move them around a little bit. Or move the mesh controls around so that we have a good idea, or we have good resolution. That is, we have fine cells where the shockwaves occur. I'm going to go ahead and edit all our free stream conditions and set this to a Mach number of 1.6. And let's keep an eye on this velocity plot for a second. So we see a whole bunch of high velocity air surge in. And we're going to see the flow field around this thing rapidly reconfigure. You can already see the beginning of a bow shock forming. This is sort of the other configuration that you'd expect to see in supersonic flow. Or one of several configurations. You could have attached shocks, you could have detached shocks, you could have surface shocks due to transonic flow effects. But the reasoning behind that's not quite what I wanted. Behind all of these is pretty much the same. You need a lot of cells where you expect shockwaves to form. If you don't have cells where you have shockwaves form, you are going to have issues. Let me just show the mesh here. So we can see that this is a little bit of a problem. Like, we have mesh refinements, but they're really not capturing where the shockwave is, right? So we would need to adjust our mesh refinement. We will adjust our mesh refinement. Let me go ahead and stop this for a second. We're going to go ahead and say, okay, how do we define this? We defined this with a big cone and a little cone. The little cone is probably somewhat too aggressive as well. We need to shift that little cone back a bit. So we're going to kick this back to something like 4.5 meters. And we're also going to kick the endpoint back to something like 14 meters. So we can see that it's pretty much clear. We're also going to drop this a little bit. So we can see that this is pretty much clear, and we're actually going to also lower. But the point is, we want this cone to be very much away from where there are strong discontinuities. Move this down, we can actually probably move this up a little bit. There we go, that's probably fine. So the important thing is, where there's strong discontinuities, it's pretty well clear of this. The other thing is, we need to move this cone up. We're going to go negative like 1.2. We're also going to kick up the end radius to something like 12 meters. Maybe not 12, maybe 10. There we go. So if we remesh this, we should mostly have captured. We're actually sitting ever so slightly on the edge here. Let's make this like 11 meters. We should have captured a lot of the, or pretty much all of the shockwave, all the way out to the edge of the domain. We can see vaguely, get rid of this. Oh, it's remeshing, so it's not going to update this. We can see sort of where the shockwave is. We want to encapsulate that in our volume refinement region, while simultaneously not including that really don't need as much refinement. Again, you've got to keep real close track of where the shockwaves are for supersonic flow. Or you have to have a good estimate of where they are and adjust your mesh as necessary, potentially even after you've started the simulation, to make sure you are capturing the shockwaves where they're forming. We're going to go ahead and let this finish, and we'll see what the mesh looks like. I fully expect the cell count to have gone up significantly. That's fine, that's expected, because we need to put these cells where we need the cells. That's the fact of it. Luckily, this is relatively quick because it's still a two-dimensional simulation. And a little bit later, I'm going to introduce a couple of more advanced topics that we can use to help make this sort of simulation less painful in 3 dimensions. In 2 dimensions, you can kind of brute force it by throwing more cells at it. 3 dimensions, that's a lot harder. But we can see that, if we zoom in here, our shockwaves are entirely encapsulated in our finer mesh region. Although it doesn't like me moving this view around too much. Which is great. This is exactly what we needed. So, these fine cells are capturing this shock quite well. That's exactly what we want. And we really don't have any of those large discontinuities anywhere outside of this refined mesh region. That is what we want from a supersonic mesh. You want to be capturing the shockwaves. Now, if you wanted to be particular about this, you don't necessarily need to refine everything in here. Properties change through here, but far less rapidly than they do at the shockwave. So you wanted to do this double cone thing a couple of times to generate one cone much more accurately where the shockwave is, you could absolutely do that. You could rotate, you can generate the cone and then rotate it with the airfoil. You can do all kinds of things. You could generate another refinement region much more accurately where this trailing edge shock is. Those are entirely valid approaches to still get cells where you need them, but reduce the overall mesh count. And that would be necessary if you were significantly limited in your cell count for a 2D simulation. Or for a 3D simulation, it's necessary in general. However, there are some more complicated techniques we can use for three-dimensional meshing that are unlocked by the virtue that 3D meshes really need a lot more control over their mesh operations. I'm not going to go over those in this video. We will go after them a little bit later here. But those are things that we can and will talk about a little bit later here. And so that is going to be the core of the next major topic of supersonic flow and advanced three-dimensional mesh refinement.